Welcome to Unit 1, Lesson 7, Adding and Subtracting Rational Expressions. So now in this lesson, we're going to continue to use all of the same skills as usual that we've been building up throughout this unit so far, which means that we may still need to remember how to restrict and simplify these rational expressions as we see them. And in some cases, we may also have to multiply and divide rational expressions as we see them. But adding and subtracting can be particularly tricky because just like when we're adding and subtracting regular fractional numbers, we need to find common denominators amongst our different rational expressions. Now, in order to help us do that though, we're going to continue to use a lot of our important skills like factoring. So we're first still going to factor the numerators and denominators, and that will, as usual, allow us to state any restrictions on the variables. And we can reduce at that stage if possible as well. But most importantly from there, we're going to use all the different factors that we see in our factored form or our simplified form and try and find the lowest common denominator, or the LCD, and then rewrite each expression using that. What's important from there is to remember then we only need to add or subtract the terms in the numerators, because we've already found a denominator that will be the same denominator for all of our terms from there. So all of the final simplifying will be done with the numerator, and then once we have that simplified numerator, we can see if there's any final simplifying we can do of the overall rational expression. That's a lot to kind of keep straight, but let's see how it works in an actual example. So with this first one here, we clearly see we have three different denominators in our three rational expressions. And all three of these rational expressions are being either added or subtracted with one another, so they all need to have a common denominator before we go any further. So just off to the side, let's think about what that would be. And we'll generally, of course, call it the LCD. What is the LCD in this case? Well, it needs to be a number, at least. It needs to include a number as part of it that can be evenly divided by the coefficients of all three of these denominators. So in other words, it needs to be a coefficient that's divisible by 2, by 4, and by 6. Well, the simplest one of those we can find is 12. What that means is that the coefficients from each of our denominators that we do have can be easily multiplied by something to get them up to 12. We also need to include the highest possible exponent on each variable that we see. So in this case, the only variable we see is x, and the highest exponent we see on it is a cube. So our LCD has to include x cubed, because, well, if the first denominator only has, for example, x to the power of 1, but that can still evenly divide with 12x cubed. The last denominator has an x squared in it, 6x squared, but that can evenly divide with the x cubed as well. We need to make sure we have that x cubed most importantly because that middle term has an x cubed in it as well. And so if our LCD was only, for example, 12x squared, there'd be no way for us to take this middle denominator and multiply it by some simple term to make it into 12x squared. But we can easily take this middle thing and multiply it into 12x cubed. So now we have to start thinking about what we would actually do in each case. What we would actually do in each case to make each of these denominators equal to 12x cubed. And when I set up my next step, I'm actually going to jump ahead to the idea that now that we know 12x cubed is our denominator, I'm going to make one great big line and put 12x cubed as the sole term on the bottom, because remember, each of our different expressions are all going to have that same common denominator, so why not write the entire thing over one single common denominator like our answer will have anyways. All the work is really going to happen on the top, in the numerator. So we have to ask ourselves, as we sort of go through this one by one, we have to ask ourselves first, if we think about the 2x that we have as the denominator of our first piece, what would we have to multiply that by to get 12x cubed? And whatever that thing is that we multiply it by, we'll multiply the top by that as well. Well, if we take 2x and we multiply it by 6x squared, that's what would turn it into 12x cubed, which means that's what's happened to the denominator, and so that's why I'm doing it to the numerator as well, which means I'm literally going to take the 2x minus 3 that I already had in my numerator, and I'm just going to multiply it, using brackets for now, by 6x squared. Now the next term. Well, the next term had a numerator of 1 minus 4x cubed, but I have to think about what would I have done to its denominator. Well, a denominator of 4x cubed could just be multiplied by the number 3, and that will get us to our common denominator. So I have to multiply that numerator by 3 as well. So I stick a 3 in front, and I put that 1 minus 4x cubed part in its own little bracket. And now I'm going to subtract some modified version of my final numerator. So 6x squared is now the denominator I started with. To get that to a 12x squared, I would have to multiply by 2x. So that becomes the extra piece that I multiply by on top, and then I put my 5 minus 9x in a bracket beside it. And now you can see I have a lot of expanding and simplifying work that I have to do on top. So let's just do that. This is all just essentially review skills on top at this stage, and I'm not going to be actually doing anything with the bottom. So I'd get like 12x cubed minus 18x squared plus 3 minus 12x cubed minus 10x, and then careful with the signs, plus 18x squared. And all of that is still over a single common denominator of 12x cubed. Well, if I do a little bit of simplifying, actually the 12x cubes on top completely cancel one another out. And the 18x squareds on top also do the same. So it actually simplifies down quite a bit to just, well, positive 3 and then minus 10x on top. And on the bottom, it's 12x cubed. So the question then, sort of the final question we have to ask, is going back to our original common denominator and any factors that we see in it. Really, our common denominator is just one single term. What about that denominator could possibly cause it to equal 0? And we need to restrict those values. Well, in this case, if x itself was 0, the entire denominator would be 0. So our restriction is that x cannot equal 0, and that's the only one in this case. Let's keep going and try another one. So for example B, if I can zoom in a little bit, there we go. For example B, we see two pieces that are clearly rational expressions, and then the third term there is just a single number, the number 2. But we have to remember that that can easily also be written as a rational expression in just writing it as a fraction itself, because fractions are very simple versions of rational expressions. So we can, instead of calling this 2, we can call it 2 over 1. And suddenly it's got a denominator as well. And now we truly are looking at 3 denominators, 2ab squared, 2b, and the number 1. And we're looking for an LCD amongst those 3 denominators. Well, in this case, we know that it needs to have at least a factor of 2. It needs to have at least 1 power of a, because that's part of one of our denominators. And at least it needs to also have at least 2 powers of b, because that's part of one of our denominators as well. But as long as it includes all of those things, which is really just the denominator of the first term, as long as it includes all of those things, it's going to satisfy as a denominator for the other 2 terms as well. Because there are simple things we can multiply each of those by to make it equal to 2ab squared. So let's make that happen in our next step. Once again, I'm actually going to just draw one great big line and put my 2ab squared on the bottom as my common denominator. And then I need to ask myself, what would I have to multiply each term's denominator by to get 2ab squared, and then multiply its numerator by the same thing? Well, again, I'll sort of back up and do these all over again. So with 2ab squared, I just have to multiply it by 1 itself to get the common denominator in this case. So you don't even really have to write this, but I'll just sort of write it in as a reminder. It's like we're going to do 1 times the numerator that we had originally, which is really just going to keep that numerator the same. Then we're going to subtract that with, well, in the next piece, we're starting with 2b, and we need it to be 2ab squared. So we need to multiply the top and bottom by an extra factor of A and an extra factor of B to make that happen. And then the B plus 2 will get multiplied by those in our next step. And then we're going to add that with what we have to do with our last term, which, well, we need to change a 1 into 2ab squared, which means we literally just multiply it by 2ab squared. And because we're doing that on both the bottom and the top, that's what's going to appear now on the top. And I multiply that by just the 2 that I have in brackets there. So let's expand out and see how we can simplify. So we have ab squared plus 2 minus another ab squared, when I start to expand that, minus 2ab, and then plus 4ab squared. That whole thing still has the same single common denominator. Give myself a little room below. And let's start to simplify. So I'm going to put my ab squareds first. I have 4ab squared. And then I have a minus 2ab. And then I still have a positive 2. It's always best to arrange your terms so that the term that has the highest exponents in it is first, and the one that has the lowest exponents, or doesn't have any variables attached, is last. So it's sort of in a descending order that way. And that's still over 2ab squared. And when I look at what I have there, it may look like I've sort of simplified it as much as I can, because you wouldn't see any more like terms that can be collected. But simplifying, remember, uses all those same skills that we reviewed a couple lessons ago, where we should still try and factor this expression further if possible, and simplify using common factors in the numerator and denominator. Specifically, what I mean by that is the top can actually be common factored. Every term can be divided by 2 to look something like this. So if I pull a 2 out in front, it leaves me with 2ab squared inside of a bracket, minus just an ab, and then plus 1 when I common factor out a 2 from all of that. And the reason why I common factored out a 2 from all of that is because I also have a factor of 2 on the bottom. So I can divide the top by 2 to leave a 1 in this place, and I can divide the bottom by 2 to leave a 1 in this place. And now I have an even simpler way to write my final answer, which I'll write below as follows. So it's just 2ab squared now minus ab plus 1. And on the bottom, I just have ab squared. So I did some simplifying there in my last step, but when I go to state my final restrictions on this as well, I should just go back to my original common denominator before any simplifications were made. Now, regardless of whether I do that in this case, the answer is pretty clear. The values that cannot be equal to 0 are both a and b. So a cannot be equal to 0 and b cannot be equal to 0. If either of them are, then that entire denominator is equal to 0, and that's one of those situations where our expression simply does not work. Let's try a couple more. So now, for question C here, if you look carefully, it looks really like we have almost the same denominator on both of these. The only difference is the second one here has the subtraction going in the opposite order. Now, one thing that's important to remember is that numbers can be added in any order, and it doesn't change the result. So 2 plus 3 is 5, and 3 plus 2 is 5. Numbers can be added in any order. But when we subtract numbers, switching around the order of subtraction actually produces the opposite, or the negative result. So for example, 7 minus 3 is equal to 4. But 3 minus 7 is actually equal to the opposite of that. It's equal to negative 4. And so that goes back to this idea that we've seen before, where we can switch around the two terms of a subtraction by just putting them in a little bracket and sticking a negative in front. So here's how I'm going to do that little trick in this case here. I'm going to first rewrite the first expression exactly as it was before, because that first expression has a denominator of x minus 3. And it turns out I'm going to be able to create that denominator in the second term. So the second term is now going to be still 4x minus 5 on top. But now I'm going to switch the order of the 3 and the x. So I'm going to put it as x minus 3. But in order to do that, when I'm switching the order of subtraction, I need to put it in a bracket and really think of the negative of that. So 3 minus x is literally the same as doing x minus 3 and then taking the negative value of that. So I can actually then from there simplify this even a little further, because now I'm going to really be adding a rational expression that overall has a negative value. So this second rational expression, because it has a negative on the bottom, means that second rational expression is overall negative. So I'm really adding a negative thing. Let's make this a little bit simpler by just making it into a subtraction statement. So the first piece stays the same, and now I can just say I'm really just going to subtract. And now I don't need to keep that negative on the bottom at all anymore. So now I just have a denominator in both cases of x minus 3. So I think it's pretty clear in this case, what is my lowest common denominator? Well, it's the common denominator that I already have. It's x minus 3. So what does that mean? Well, in this case, it means I can, I should do this in the same color I've been using all along. It means that my next step is going to have just one single common denominator, and I can really just start to put these terms together. So it's going to be x plus 4, but then I need to subtract the entire numerator of the second one. So that means I need to be careful with the signs. I'm subtracting 4x, but then I'm subtracting negative 5. Well, subtracting negative 5 means I'm really like adding 5 extra ones on. So simplify that. Well, it's going to become negative 3x's, and then we have plus 9, and it's still over x minus 3. So now we've done as much simplifying as we can to our numerator, but now we can't assume that we're done. We need to take a full look at our overall expression, including its denominator, and see if we can factor any further to allow us to simplify further. And in this case, once again, just like our last one, the numerator actually does common factor. We can common factor out negative 3, and that leaves x minus 3 in a bracket beside it, which, coincidentally, is exactly what our denominator is. So what does that mean? Well, it means we have this common factor occurring on top. We have an x minus 3 on top, so I can divide the top by x minus 3 and leave a 1 in this place. And I divide the bottom by that entire same factor as well, and it leaves a 1 in its place also. So what does that mean? Well, it means my final simplified rational expression is just the number negative 3. So it's nice that it did simplify that beautifully for us, but we have to keep in mind that before it was simplified, there still were variables involved, and there were variables involved in our denominator. So we still, even though we've been able to reduce it away in our simplification, we can't forget that x in this case still cannot equal 3. And if you're wondering where I got the x equal 3, remember that x minus 3 can't equal 0 because that was our original denominator. So x cannot equal 3, so that our denominator will never be 0. And as long as that condition holds, as long as that restriction is always true, then it turns out this very complicated expression we started with at the very beginning of question C ends up simplifying down to just a single negative integer in this case, negative 3. Let's do one more of this type. So now we've got trinomials all over the place in our numerators and denominators in some cases. So that means we've got a lot of factoring we've got to do. So these factoring steps I'm going to start doing much quicker than I normally have in the past. I'm just going to jump right ahead and show you what my factored forms are. On the bottom, it actually factors into x minus 2 times another x minus 2. So I'm actually going to factor that as x minus 2 squared. And then in this next rational expression that's being subtracted, both the top and the bottom can be factored as tricky trinomials. So this is what I got for mine. And now, before we try and find a common denominator, we should always try and simplify these individual rational expressions first, because the subtraction step is trying to start combining these rational expressions, but we should make them as simple as possible first before we even do that. So, as usual, let's look for some common factors. Well, we see that here we have a 2x minus 5, so we'll reduce that to a 1 as long as we divide the bottom by 2x minus 5 and reduce that to a 1. Now, we'll have to keep that in mind, though, when we eventually state our restrictions. So even though I'm reducing and getting rid of this now, that 2x minus 5 still cannot equal 0, so that's going to be one of our restrictions that we state later. You can write this in a simpler way now. And really, I don't even need to put the top and the bottom in brackets anymore. I did just sort of out of habit, but you can leave them off in that case when you only have one factor on top and one on the bottom. Well, our first big rational has two factors of x minus 2 in its denominator, whereas our second rational just has one factor. But that means as long as we include two factors of x minus 2, that's going to be our LCD. So our LCD in this case is x minus 2 squared. And again, the reason why that is because, well, obviously this denominator is already x minus 2 squared, so we don't have to do anything to change it to that. And this one can be easily changed into x minus 2 squared by just multiplying the top and bottom of its rational by another factor of x minus 2, which is what we'll do in the next step. So the first rational expression, this one overall, is really just being multiplied by a 1 on top and bottom, whereas this one is going to be multiplied by x minus 2 on top and bottom. So because the first one's just multiplied by 1, I'm not even going to write a 1. I'm just going to say that it's 2 minus 5x. But now the 3x plus 1 has to be multiplied by an extra factor of x minus 2. And as long as I do that, then I have the entire thing over a single common denominator of x minus 2 squared, or two factors that are each x minus 2. So from there, this is where I want you to try and finish this one off. So just a reminder, before you go any further, you're really just simplifying the numerator at this stage, but before you do too much with that, you'll need to first expand by multiplying these two brackets together to find all the different terms that are created from that, and then simplify it along with the other two after that. Once you've done that, you can go to the original version of the note to check it. And in the second portion of this lesson, we'll do a little bit more complex examples where the factoring and the factors involved just take us a little bit further in this process.